Hello, everyone, and welcome back to our series on urban energy modeling with Dragonfly. And I know in the previous video I said that we'd be looking into other workflows for creating urban models from different geometry sources. But before I get to those videos and that topic, I want to take 1 second and look at a new capability that we've added since the original series. And if you actually check the date of this video, this one's been released a little bit later than all the other ones in the series. And you'll notice that the versions of my components are actually from a newer version too. And so I wanted to take a pause just to show you this new capability that's been added that is specifically about operational carbon capabilities. So if you remember in the previous video, we looked at the energy use intensity, the EUI of our entire district here, and we used this little HB end use intensity component. And while I'm at it here, why don't I make sure that we all can see the names of these components, right? I'm going to use my little plugin here to make sure you can see the name end use intensity. And so we're going to use a workflow in this video that's very similar to the previous video. But instead of looking at end use intensity, which if you remember is the sum of both the heating fuel energy like natural gas and electricity divided by the floor area of all the buildings, right? We're instead of looking at this end use intensity that kind of mashes these two very different types of energy sources together, we're going to look at operational carbon, which is going to allow us to weigh the importance of reducing heating fuel usage, let's say, against the electricity usage of things like cooling or electric equipment, right? We'll be able to get a much better sense of the overall environmental impact of our buildings, or at least the impact of our buildings on climate change through this lens of carbon intensity. So first thing is first, if you guys have Ladybug Tools 1.6 or above installed, you'll notice that there is a new component under the 6 result tab of Honeybee Energy, and this is simply called HB Carbon Emissions Intensity. If I drag and drop this component on the canvas here, you'll see that it's very similar in principle to the EUI component we used previously, in that it takes a list of SQL files as input or a single SQL file if you so desire. But instead of giving us out the EUI, right, the energy use intensity, we're going to get a CEI, or carbon emissions intensity. And the units of carbon emissions intensity, if you hover over the output here, this is going to be in kilograms of CO2 per square meter of building floor area. So the denominator of these units are the same as EUI, right? It's still the gross floor area of our buildings. However, right, instead of looking at kilowatt hours of either heating or electric fuel, we're going to be looking at CO2, kilograms of CO2 put out into the atmosphere annually by our building energy usage. So, all right, so let's go ahead and start looking at the carbon intensity here. So I'm going to connect up my SQL output from our run simulation over to the carbon emission intensity component here. And you'll see that there's one other required input for this component, right, in addition to these SQL files that actually contain those energy use results, right? If we click on the balloon here, it tells us that we need to plug in an input for location or kg megawatt hour, right? We need to basically supply an input here in order to get the component to run. And you'll see that if we are within the US, as we are with this example file, we actually have embedded within Ladybug Tools a data set of carbon intensity of the electric grid for various locations throughout the country, throughout the United States. And so actually, if you are working within the US, you can simply plug the location object from your EPW file into this component, and will automatically have the carbon intensity of the electric grid for that location ready to go without anything else needed. If you are one of my friends who are not inside the U.S., I apologize that that they're still working on the database to have the carbon intensity of the electric grid across the world. So maybe in the future we will have support for that. But if you are international, you can still use this component. You just have to know the carbon intensity of your electrical grid in kilograms of CO2 per every megawatt hour of electricity produced. And more often than not, you can usually find this information online if you just search for the carbon intensity of your electric grid. I know, for example, I looked at a few different locations. It'll certainly vary a lot depending upon your country. Most developed countries will probably have something, within the range of what you see if you hover over the input here, right? About 400 kilograms of CO2 per megawatt hour. This is about the average US energy mix around 2020. I've certainly seen other countries, though, like I think I remember looking at France's electric grid intensity, and because they're majority nuclear power, I think I remember it being somewhere really low, around 50 kilograms. So again, it's going to vary a lot place by place, but hopefully also these numbers that are in the input description here will give you a guide. If you know roughly where your country is in terms of implementing cleaner sources of energy, you can probably estimate what that electric carbon intensity is. But all right, because we are in Buffalo, New York here, right? We have a location. In fact, instead of using this location, I'm actually going to bring it straight from the EPW file because that will have more reliable information about the actual state that the city is located in, the city of Buffalo. So I've just went over to my Ladybug tab. I grabbed this LB import location onto the canvas, and I'm going to connect up the EPW file, the same one I used for the simulation, to this component. Right, and this will give me the location on the globe here, basically, and importantly includes the state, which is how this is identified here. So if I go now and I connect up this location input to this component, it's going to now import all the carbon intensity information from the SQL using basically this location as a way to estimate the carbon intensity of the grid. And there's one more important input that I just want to mention here quickly, which is that you can select what year in the future the projected carbon intensity of the electric grid will be. Obviously, right, we are moving towards cleaner sources of energy for our electric grids pretty much worldwide. So, right, so as you move forward in time, this is going to get cleaner and cleaner. The carbon intensity of electricity is going to diminish. You'll see the default years is 2030 because we want to look at least a little bit into the future, but it's difficult if we get. I mean, you can go all the way up to 2050, but at that point it becomes more and more speculative of exactly how close these projections will get. So in this case, right, I'll just stick to 2030 in this case, and let me pull up a panel here so I can actually look at what the carbon intensity is. And you can see, right, so these, by default, this is in SI, right, it's in kilograms of CO2, right, and you can see, whereas our energy intensity was about 188 kilowatt hours per square meter, our carbon intensity is about, let's see, that's 33.7, and this is going to be in kilograms of CO2 per square meter of floor area, right? And so I'm just putting the units there so I don't forget them, right? So you can see these units, they certainly have a relationship to one another. As the EUI goes up, the carbon intensity will typically go up as well. I'd be very surprised if it didn't, but these are different units here. And you can see, just like the compute EUI component, we can look at the end use breakdown in terms of carbon. So I'm actually just going to copy and paste both of these panels that I used here to look at the breakdown of end uses, basically in terms of energy. I'm going to copy those, but I'll connect up the carbon intensity end use, and then I will connect up these end uses, which is actually just the same we can see here. Right, and this now gives us a new type of insight into what exactly was driving the energy use of this district. Now you can see, I think I also updated some of the templates here for the building types since the previous video, but I think in the previous video still the heating was the biggest term of energy use, followed not too far by electric equipment. I guess it's the next biggest one. I guess it is pretty far behind because it's roughly half of this here. But what we can see certainly here, well, if heating was the biggest source of energy use intensity, we see it's still by a long shot the biggest source of carbon intensity. And in fact, it's a huge, huge source. It accounts for, it looks like, more than 2/3, I think, of the entire carbon consumed by these buildings in 2030 is going to be from the heating systems, basically. And a lot of that comes back to our decisions about our HVAC equipment that we decided to choose here, right? Pretty much all of these are using boilers, right? All of these are using gas boilers. And so those are going to be significantly more carbon intensive than the electric grid, especially by 2030, and especially in a place like Buffalo, which I know is right next to Niagara Falls and has a huge amount of hydroelectric power. So I don't think this is terribly surprising, but this really gives us a lot of insight, right? That whereas, like, if we were to try and focus on just reducing energy use, it might point us in a few different directions of both reducing heating, maybe also reducing lighting with some LEDs. But we can take, when we take a step back and look at carbon intensity from this perspective, right? If we want to pick the term that is going to be most impactful for reducing the greenhouse gas emissions of these buildings, by a long shot, it's heating. And probably we can reduce this a lot simply by swapping out those boiler systems with heat pump systems. Most of those templates that we have here, right, for like a VAV system, there are options for these with air source heat pumps, which I'd encourage you all to try out if you have time. And you'll see that the carbon intensity will go down by a long shot because we're replacing that fossil fuel with electricity in that case. And also you have to account for the fact that the electricity consumed by an air source heat pump, right, you're actually getting several units of heating per unit of electricity supplied to that pump. Right, so that is by, I'd say, a long shot, one of the biggest things that we can do to really reduce the carbon intensity of this particular district here. Second to that, we can see things like, well, interestingly, like the gas equipment, right? It's interesting to compare electric equipment and gas equipment, right? Because we can see electric equipment makes up way more of the energy use than the gas equipment. But when we take a look at this in relation to the, into the carbon intensity here, right? The gas equipment is actually a lot more impactful than that electric equipment, right? In terms of its, well, I shouldn't say it's, there's still more carbon being produced for the electric equipment here, just like there's more EY for the electric equipment than gas equipment. But whereas the difference between these two is like a factor of 10, right? The difference between these two is like a factor of 3. So if we, replacing those gas stoves with conduction stoves or something like that, right? Those gas stoves in those restaurants, that'll probably also go a long way to reducing this carbon intensity. All right, and maybe just to show you guys, what this year input can do here, right? If right by default it's 2030, but if you really want to look at, something more contemporary, like, I'm making this video in 2023, you can plug in that, or, better yet, I can actually do the specific year. I think here. Oh, actually, it's going to tell me. Yeah, it's so we don't have data for certain specific years. I believe we have it either. Yeah, we have it for every 2 years. Basically, we have projections for electricity. So you will have to choose an even number of year. But right, you can see certainly the carbon intensity today around 2022, 23. This is a lot more than what it's going to be in 2030, right, which is the default. Right, you can see, right, a lot of the projections of carbon emissions, and these are based on studies that have been conducted by several economists, right? And this kind of makes sense because wind power is one of the most cheapest forms of electricity. It's the fastest growing one in the U.S. right now, and I think a lot of these projections were even made before things like the Inflation Reduction Act went into the U.S. So this may even be even more ambitious right now. But right, you can see by 2050, if we go all the way there, actually, wow. So interestingly, probably the majority of the decarbonization of the electric grid is probably happening within the next 10 years. I guess is projected to happen in the next 10 years, at least for this location in Buffalo, New York. And maybe, again, that may have to do a lot with things like abundant hydroelectric power that they have there. But anyway, each location will be different. I'd encourage you to play around with this year if you can. And of course, right, if you are in a different country, and let's say, let's say that we're in France, and I remember this, the carbon intensity, I think, was around 50 or something like that, something very, very low, right? You can see that the carbon intensity of everything would be a lot lower, and it's almost all heating and gas equipment at that point. Oh, and water systems too. Oh, that's a really good point, because the water systems actually by default, I think that we put here, if we assign them, we assigned a gas water heater. So, right, so we can actually, if this really puts things into perspective, right, of that, after we've decarbonized a lot of the grid, the key things that we need to take out of our buildings, they're going to be those boilers, they're going to be those gas stoves, and they're going to be those hot water heaters that are still using gas. And this brings it all really to light here. So, all right, well, let me disconnect that. I'm going to put the location back here, right, and we can say this is one way of actually looking at the carbon intensity. But I will note quickly that there's an important disclaimer to this carbon intensity here. You can probably understand it from the fact that you can just plug in a single value for the carbon intensity of the electric grid and get out the intensity. The limitation is that there's really only an average carbon intensity of the electric grid being used inside this component. And in reality, right, the electric grid is not something that is static, right? The relative intensity, the carbon intensity of the electric grid is something that will change over time. And especially when you start to hit certain conditions, like let's say after sunset, when everybody goes home and turns on their lights and their TVs and starts cooking, and and the air conditioning use may go up if it's the summer, right? We tend to get these peak electrical demand conditions, which will oftentimes, more often than not, cause us to turn on some of our most dirty fuel sources, right? We're going to fire up those gas turbines in the power plant in order to try and meet that demand, that peak demand. So the important thing to remember here is that a building that is using most of its energy during that peak time is certainly going to be dirtier than a building that is using most of its energy at, let's say, 5 a.m. or sometime when not everyone else is using all the energy. And so if you really want to account for this, there is a workflow, but I should again give another disclaimer for this, that this workflow is only for the US right now. But there's a workflow that will allow you to visualize and calculate this hourly carbon intensity of your buildings and of your district here. And so in order to do this, you'll notice that there's this new input if you have URBANopt or if you have Ladybug Tools 1.6 or above installed, there's this new input for emissions year. And just like this component here, right where we plugged in a year, you can plug in a year to this component. And if you're in the US, this will actually write hourly carbon intensity values into the SQL files that we're getting out here. And we can bring those back into Grasshopper to visualize those. So that's what I'm going to do right now quickly. I'm just going to pull up a panel. Well, let's say we'll look at 2030 here, which was a good default in the other case. And if I go and I plug in this input for emissions year, it's going to rerun the simulation, but this time it's going to keep track of the hourly carbon emission intensity. So I'm going to fast forward here because it's going to rerun the whole simulation. It's going to take a few minutes, but I'll meet you on the other side and we'll actually parse some of this carbon intensity, this hourly carbon intensity into Grasshopper so I can visualize it for you. And you can at least get a sense of what it looks like when you actually account for this hourly grid intensity. Okay, and we're back. And that took a few minutes on my machine. Hopefully it wasn't too bad on yours as well. And so now that we've actually rerun the simulation, these SQL files that we looked at before that are responsible for bringing in our energy use intensity right here, these SQL files will now contain hourly carbon intensity results. So the easiest way that we can bring these results into Grasshopper here is if I go back to the Honeybee Energy tab, and I drag and drop this component on the canvas called HB Read Custom Result. So this works just like the other result parsing component that you saw in the previous video, except that it can import any type of output that you want from Energy Plus, as long as it's something that you actually requested from the simulation. And in this case, because we plug in an emissions year here, we actually have an output now that is called future hourly electricity emissions, which I can plug into this input here in order to bring that data into the Grasshopper environment here. So that's what I'm going to do first. So let me actually bring up a panel that has the name of that output. And importantly, the name of this output is a little bit different than certain other Energy Plus outputs in that it has underscores instead of spaces. But let me just see if I can remember it here. So I'm going to bring up a panel by typing double quotation marks after double clicking on the canvas. And I'm going to type future underscore hourly electricity. I think I spelled that right. And then underscore emissions. Okay, and if I hit enter, right, I believe I spelled this correctly. So this is what it should look like, right? The name, the Energy Plus output that I want to bring in here. And again, I know this is a little implicit because you don't necessarily know, although actually if you hover over this input, actually it does tell you the name of it, future hourly electricity emissions. And so I can go and I can connect up the SQL files to this component. I can connect up the name of this Energy Plus output that I want to bring in here. And after I give it a few seconds, or actually this really only took a second or two to run, you'll see that I now have, coming out of this component, a series of hourly data collections. And it looks like I have one for each building that is going to contain basically the carbon emissions. In this case, it looks like in megatons of carbon for these buildings here. And just like what I did in the previous video, instead of trying to look at individual data collections, it'd be nice if I can sum all of these together so that I'm just looking at a single list of hourly values that show me the carbon intensity. So that's exactly what I'm going to do right now. I'm going to use the same component I used in the previous video that was called a Ladybug Mass Arithmetic Operation. So let me drop this on the canvas here. And let me go and plug in the results. Basically, I'm going to plug in these 13 data collections to the data here. And you'll see right out of this, we'll get a single data collection of 8760 hourly values for the future hourly electricity emissions. Maybe I'll just overwrite the type to make this a little clearer, just like I did in the previous video. And I'll call this carbon emissions. Right, that'll just make it a little easier to preview in my visualizations, right? It'll have that name carbon emissions attached to it. And certainly I could deconstruct this data collection and look at the individual values, but it's probably going to be most helpful to look at this on an hourly plot. So I'm going to drag and drop this Ladybug hourly plot component on the canvas here, and I'm going to connect up my hourly data collection to it. Then you'll see if I go over to the Rhino scene, let me see, I may have to zoom in or out here. Yeah. All right, well, I got a lot of things previewing on top of each other at the moment. Maybe I will change the base point of this chart so that it's not on top of my my simulation geometry there. So I'll just very easily bring up a panel by typing double quotation marks. I'll type minus, or let me see, I'll do 0, comma, minus 300, comma, 0, and hit enter. And if I plug that in for the base point, that should move it about 300 meters to the south of my district, so it's not overlapping with it. And you know what? It's probably going to be a little easier if I switch into top view. So let me do that now quickly. All right, we can see very clearly, right? We have megatons of carbon, and it looks like the maximum number of hourly megatons is about 2.7. And very interesting, right? You see that that maximum carbon intensity is probably not happening when there's the peak electric demand from our district, right? Instead, it's happening at around looks like 8 p.m., 8 or 9 p.m. No, actually probably more 8 p.m. Right, and in the middle of July and August, and we can kind of understand, right? That's the time of peak electric demand for most locations, right? Is in the middle of the summer, soon after sunset, when all the air conditioning's on, but everybody's cooking and got all their appliances on at home. So that's basically when all the gas turbines are being switched on, and that's why the carbon intensity of the grid is going up so much. Just to really drive this home, though, I'm going to also import another result from this simulation here. I'm actually going to import the electricity consumption of each entire building using another Energy Plus output that I know of. And that name of the Energy Plus output is just called electricity facility. All right, so I'm just going to bring up a panel with this in it. And if you can't tell, this is a much more of a native Energy Plus type of output here. Right, it uses like certain conventions like colons and stuff like that, but you can import it all the same. So in order to import it, I'm going to again grab our read custom result component. I will connect this up to the output name, and then I will connect the SQL files up to this component. And again, this took pretty quick to run, but if I bring up a panel to look at what I've actually imported here, so I think I still have a, oh, interesting. Maybe this is not the right name of the input. Let me try this again. Actually, and this is a really good point to make. So if you guys input the wrong output, you'll see the component doesn't throw an error. You're just getting nothing out of it. So if this happens, you should check your spelling. And in this case, I could see that I misspelled electricity. That should have at least another I there. So I think now if I do that, yeah, okay, it's taking a little longer to run. And you can see now I get out a data collection of electricity for each and every one of these buildings here. Now you'll see because I ran this simulation at a time step of 1, I also get an hourly data collection. Whoops. So I'm getting 8,760 values in each one of these. If you had run this simulation at a different time step, you may have like a 10-minute data collection instead of an hourly data collection. And you could easily convert that into an hourly data collection using this component called LB convert to time step. Right? This can actually take any data collection and change it to be hourly or sub-hourly or whatever you want. So that's what, if you guys have run an energy simulation at a time step other than 1, that's what you should use here. But because this is hourly as it is, I'm just going to keep it the way it is. And I'm going to copy and paste my mass arithmetic component so that I can make I got to copy paste the component too, so that I can make another version of it here, except this is going to be electricity. And let me spell it correctly this time. Yes, electricity. Right, and I will plug in my list of data collections to this. Out of the component, I should get a single data collection, right, because it's all been summed together. And I can just hold down Shift now and connect up this electricity data collection to the same hourly plot. And you'll see now I'll get the two side by side next to each other. And lo and behold, just like I told you, right, the peak electric consumption is actually not, it's misaligned with the peak carbon consumption, right? Because peak electric consumption seems to be happening sometime in the afternoon or so, which is probably pretty reasonable for a district that has things like hospitals and offices like what we have here. But really importantly, right, it's because of all those gas turbines being switched on that the carbon intensity of this time period goes up so much. So this is just so you guys have a sense. I realize not everybody, if you're outside the US, you won't really be able to use this built-in workflow of just plugging in emissions year here. If you guys are using an EPW file from outside the US, you just won't get anything from these components if you try to import those things. So I'm sorry about that. I hope in the future we can extend the database so that you can get visualizations like this. But honestly, if I'm really telling you the truth, most design decisions you can make honestly, this average carbon intensity being used here is good enough for comparisons. And so I would trust this. I would still use this for most of my studies if I were to, let's say, try and give a client an example of what their carbon intensity would be under different situations. This is really good enough, the average here. And this was more just to really show you that if you really want to do due diligence and do like a production level type of simulation, right, it is possible. There are hourly values of carbon intensity that maybe you may be able to find for your location. All right, so with that, I think we've kind of covered the most important outputs that you get from the simulation here. So in the next video, we finally will return to other workflows for creating energy models and creating Dragonfly models from different geometry sources. So just thanks for making it through this video, and I look forward to seeing you in the next one.